This is number 1 of practice set 2 in the momentum unit. I'm going to go through this to help you get started on this problem. So first off, it says the scenario is a 50 kilogram guy running to the right at 3 meters per second crashes into a 100 kilogram guy running at 3 meters per second to the left. After crashing into one another, the 50 kilogram guy flies backward to the left at a speed of 5 meters per second. The first thing I want to do is draw a picture of the situation. So I drew this purple dot right here to represent the mass of the 50 kilogram guy, and he's going to the right at 3 meters per second. This pink dot here has a mass of 100 kilograms, and its arrow is pointing to the left, and its velocity is negative 3 meters per second. It tells me after the collision, the 50 kilogram guy flies backward, which is leftward, at a speed of negative 5 meters per second. The 100 kilogram guy I know is going to bounce to the right, but I'm not sure of his velocity, so I just put V with a question mark. Next up, I fill out my if diagram. And the 100 kilogram man, the 50 kilogram man, and the total are the items that I have listed there. They're also the items in my system. Initially, the 50 kilogram man has a momentum of 50 kilograms times 3 meters per second. So that represents 150 kilogram meters per second. I've scaled my if chart to say that one box equals 100 kilogram meters per second. So I filled out 1.5 boxes for the 50 kilogram man. The 100 kilogram man has a velocity of negative 3, so his momentum is a negative 300 kilogram meters per second. So again, using my scale, I shade in 3 boxes to the left. Positive 150, negative 300, the total is negative 150, so I've shaded 1.5 boxes to the left. Finally, my 50 kilogram man has a velocity of negative 5, so negative 250 kilogram meters per second, so I've shaded 2.5 boxes. Now you might be wondering how I filled in this remainder. The total initial and the total final has to remain the same. That's the law of conservation of momentum. So I shaded 1.5 boxes to the left for the total, which means that the 100 kilogram man must have a momentum that is equivalent to 1 box to the right, or 100 kilogram meters per second. Now I have to show my math work. In order to solve for the final velocity of the 100 kilogram man, I have the momentums initially of the 50 kilogram man plus initially of the 100 kilogram man set equal to the final velocity of the 50 kilogram man plus the final momentum of the 100 kilogram man. The V is the variable that I don't know. Using just a tiny bit of algebra, I can solve the V to be positive 1 meter per second. Next up, I want to look at the energy stored kinetically. I can recall from the last unit that EK equals 1/2 mv squared. 1/2 mass of 50 kilograms, velocity of 3 squared, plus 1/2 mass of 100 kilograms, velocity of negative 3 squared. Now you have to realize that when this velocity gets squared, it's a positive value. So I have 225 joules plus 450 joules for a total of 675 joules. Finally, I've got the 50 kilogram man and his velocity is negative 5 meters per second. So 1/2 50 times negative 5 squared, plus the 100 kilogram man is 1/2 times 100 times 1 squared. So that equals 625 plus 50, 675. You'll notice that these are equal. Sometimes they are and sometimes they are not. So my LOL diagram, I showed that the 50 kilogram man had some energy stored kinetically, the 100 kilogram man had some energy stored kinetically, and finally the 50 kilogram man had a little bit more energy stored kinetically, and the 100 kilogram man had a very small amount of energy stored kinetically. I was able to determine that this collision was elastic because the EK initially and the EK finally is the same. If EK is conserved, it is an elastic collision. I hope this helps you get started on practice set 2.